In this lesson, we're going to talk about redox stoichiometry. In a redox titration, a known concentration of an oxidizing agent is used to find an unknown concentration of a reducing agent, or vice versa. The apparatus and procedure is the same as a titration with acids and bases. Instead of having an acid or base in an Erlenmeyer and an acid or base in a burette, we're going to be using oxidizing agents and reducing agents. For example, some applications of redox stoichiometry is finding the iron content of water or to find the amount of vitamin C content in various foods or drinks. In this lesson of redox stoichiometry, there's actually no new material. We are going to take balancing from the last lesson and mix it up with stoichiometry from Chemistry 2202. As such, if you're still having difficulty with balancing acidic or basic solutions, you should go back and review that lesson before you proceed with this one. The general steps that are involved in a redox stoichiometry or a redox titration is as follows. 1. Balance the redox equation. Unless otherwise specified, you should balance it in acidic solution. If it doesn't tell you how to balance it, then you should just automatically balance it in acidic solution. 2, you should organize the data for what's given and what's required. Write it down and under the species. 3, find the number of moles. You can, if the volume and concentration is given, use number of moles equals C times V. If the mass is given, find the number of moles using mass divided by molar mass. So the division sign is missing there, and you should add that to your notes. 4, use the mole ratio to find the number of moles required. And then finally, actually answer the question. So we're going to go through an example now. In the following example, it involves a titration of a solution of sodium oxalate with a solution of potassium permanganate. We're asked to find the volume of a 0.2 molar solution of permanganate ion, which will react with 50 milliliters of a 0.1 molar solution of the oxalate ion. In a question like that, you would be given this equation. I do believe it was mistakenly left off your notes, so you should add it to your notes and in brackets say that it's been given, so that when you go back to restudy this for the exam, you'll know that it was supposed to be given to you and it's not something that you would be expected to know. So given this, you should be able to look at this right away and see that it's not yet balanced. We have 2 carbons on the reactant side, there's only 1 there on the product side, and that should be a hint to you that we need to go through step number 1. We need to balance. It did not tell us in this how to balance it in acidic or basic solution, so balancing in an acidic solution will be fine. So to recall, we have to break them up into their 2 half reactions. Step number 2 is to balance for all atoms other than oxygen and hydrogen. We have 1 Mn and 1 Mn, 2 carbons, but only 1 carbon here, so we need to put a 2 out in front. Step number 3 is to balance for all the oxygens by adding water. We have 4 oxygens on the reactant side, so we add 4 H2O to the product side. We have 4 oxygens here, and 2 times 2 is 4 there, so those have already been balanced for us. Then we have to balance for the hydrogens by adding H positive. We have 8 hydrogens on the product side, so we add 8 H positive to the reactant side. There's no hydrogens in the second half reaction. Then we need to balance for the electrons. The overall charge on the reactant side in the first half reaction is 7 positive. The overall charge on the product side is 2 positive. We always add electrons to the higher number, and we need to add 5 to go from 7 down to 2. We'll do the same thing with the second half reaction. We have an overall charge here of 2 minus, 0 on the product side, so we'll add electrons to the product side, and we would need to add 2 to go from 0 to 2 negative. The next step is to ensure that the total electrons gained, is equal to the total number of electrons lost. That's not the case, so I'm going to multiply the first one by 2 and the second one by 5. So 10 electrons plus 16 H positive plus 2 MnO4 negative goes to 2Mn2 positive and 8H2O. And we have 5C2O4 2 negative goes to 10 CO2 plus 10 electrons. You should now cancel out anything that can be canceled or simplify what can be simplified. These 10 electrons would of course cancel out. And that's the only thing here that can be simplified. So we'll write our overall reaction. 16H positive plus 2 MnO4 negative plus 5 C2O4 2 negative goes to 2 Mn2 positive plus 10 CO2 plus 8 H2O. And we've now balanced this in acidic solution, and that will suffice for the balancing portion of the stoichiometry question. Now we should write down what we have and what we've been asked to find, because I find that makes it a lot easier to see how to proceed with the question. We're asked, find the volume of MnO4. So volume, question mark, of a 0.2 capital M solution. So you should at this point in your chemistry career be able to look at 0.2 capital M solution and know what piece of information this is. Is it the mass? Is it the molar mass? Is it the volume? Is it the moles? Is it the concentration? And so on and so forth. And you should know that if you have a capital M as a unit, that it is concentration. It just represents moles per liter. Which will react with 50 mils of a 0.1 molar solution of C2O4. So volume here is 50 milliliters, and the concentration is 0.1 molar. Looking at this now, you should ask yourself, well, what do I have enough information to solve for? And you should see that you can find the number of moles of C2O4 2 negative using C times V. Concentration is 0.1 molar. Volume is 50 milliliters, but of course we're not going to use milliliters. We need to use liters, 0.0500 liters. Make sure you keep those two zeros because they are significant to give us 0.00500 moles. Now that we have the number of moles of C2O4 2 negative, we can find the number of moles of MnO4 using our mole to mole ratio. If you can't remember what that is, it's the number of moles required is equal to the number of moles given times the coefficient of the required over the coefficient of the given. So we have 0.00500 moles of C2O4 2 negative times the coefficient of the required. We're required to find the volume of MnO4 2 negative. It has a coefficient of 2. We were given all of the information of C2O4 2 negative. That has a coefficient of 5. So on your calculator, you're going to take 0.00500 times 2 and then divide by 5 to give us 0.00200 moles. And we can finally answer the question where volume is equal to number of moles divided by the concentration. We have 0.00200 moles from the step above, and the concentration we were told in the question was 0.200 moles per liter. You divide that out into the appropriate number of significant figures, we get 0.0100 liters as our final answer. So as you can see from this example, nothing new. We have to balance, and then we have to do the stoichiometry from 2202. Before we proceed with example number 2, or the second example, there is also another typo in this question as well. It should say a 23.30 milliliter sample of not K, but just MnO4 negative solution is decolorized by 0.111 grams of oxalic acid, and therefore in the overall it should say MnO4 negative. So we've been given a equation. We can tell right from looking at it that has not yet been balanced. I don't see any H positives or O negatives, so it has not been balanced in acidic or basic solution. So we're going to proceed and do that. We're now going to break this up into their two half reactions. So we have MnO4 negative goes to Mn2 positive. And we have H2C2O4 goes to CO2. Now we have to balance for anything other than oxygen and hydrogen. We have one Mn and one Mn. We have two carbons but only one here. So I'm going to put a 2 out in front, just like in the last example. Now we have to balance for oxygens by adding water. In the first half reaction, I have 4 oxygens here, so I add 4 water to the other side. Here I have 4 oxygens, but 2 times 2 gives me 4 oxygens, so they've already been balanced, just like again in the last example. Then we have to balance for the hydrogens by adding H positive. I have 8 hydrogens here, so plus 8 hydrogens on the reactant side. In the products, I have 2 hydrogens on the reactant side, so plus 2 H positive on the product side. Now we have to balance for the charge. Looking at the first half reaction, the overall charge on the reactant side is 7 positive. On the product side, we have 2 positive. So just like in the last example, we're going to add 5 electrons to the reactant side. In the second half reaction, we have an overall charge of 0. On the product side, we have 2 positive. So we're going to need to add 2 electrons to the reactant side in order to balance this out. If you're still having trouble with balancing these types of equations, you really need to identify yourself so that we can get that all straightened out. Now we have to make sure that the electrons gained equals the electrons lost. In order to do that, I need to multiply the top by 2 and the bottom by 5. This will give us 10 electrons, 16 H positive, 2 MnO4 negative goes to 2 Mn2 positive plus 8 H2O, and 5 H2C2O4 goes to 10 CO2 plus 10 H positive plus 10 electrons. Now we need to cancel whatever we can cancel. 10 electrons and 10 electrons cancel. We also have to see if there's anything that we can simplify. We can get rid of all 10 of those hydrogens, and that will leave us with just 6 on that side. So my overall balanced equation, we have 6 H positive plus 5 H2C2O4 plus 2 MnO4 negative goes to 10 CO2 plus 2 Mn2 positive plus 8 H2O. We've now balanced, so we should write out what we have so we can see how we need to proceed with the stoichiometry. We have a 23.30 milliliter sample of MnO4 negative. And we have 0.111 grams of oxalic acid, so that's the mass. And we're asked to calculate the concentration of MnO4 negative. So at this point, you should ask yourself, what can I find? What do I have enough information so that I can calculate the moles? And it should be evident that you can find the number of moles of H2C2O4 using mass divided by the molar mass. We were told that we had 0.1111 grams of the oxalic acid, and you should calculate the molar mass. And when you do, it would be 90.04 grams per mole to give us 0.001234 moles of that. So that would be 1. Then we can always find the number of moles of anything else. So we need MnO4 negative by using the mole-to-mole ratio. 0.001234 moles of oxalic acid times the coefficient of the required. We're required to find the concentration of MnO4. It has a coefficient of 2. We were given information about oxalic acid. It has a coefficient of 5. So on your calculator, you should take 0.001234, multiply it by 2, divide by 5, and you get 4.936 times 10 to the negative 4 moles. Once you have the number of moles of that, you can finally answer the question, finding the concentration using moles divided by volume. We have 4.936 times 10 to the negative 4 moles, divided by a volume in liters of 0.02330 liters, to give us a final concentration of 0.02118 molar. Do not forget your units. This is the process that you must follow for these types of questions, so you can now go ahead and work on the worksheet.